Hi, welcome to Calculus. Today we're looking at section 8.4, integration of rational functions by partial fractions. So what we are looking at here are problems like this one. The integral of 5x plus 8 over x minus 2 times x plus 4 dx. Now in this particular case, the denominator is already factored. You might have to do the factoring to get it to look like that. All right, now you can see I finished the integration here, but we're missing some stuff, and that's all right behind me. So what we're doing here is we're going to take this big fraction and we're going to split it up into two smaller fractions, which in this case end up being 3 over x minus 2 and 2 over x plus 4. So this is called using partial fractions. We're going to try and figure out what two fractions would be the same thing and make our lives a lot nicer. So it turns out that the process here, relatively straightforward, but it can be very messy. So I'm taking the big fraction that I started with, and because I have two factors on the bottom and they're both just plain linear factors, I know it's going to decompose into two separate fractions. So I have a over the first factor on the bottom, x minus 2, plus b over x plus 4. And so our goal is to figure out what a and b here have to be so that we can take it back and do all this fun stuff that I did over here. So here's what we do. We multiply everything by the common denominator. So the common denominator is just x minus 2 times x plus 4. On the left-hand side, that means the denominator goes away. We just get 5x plus 8. And then for each of these fractions, one of those two pieces goes away. In this case, the x minus 2 goes away because it would cancel out, leaving us with a times x plus 4 and b times the x minus 2. So this is a wonderful little equation. We really want a and b, so what we can do is we can pick values for x, anything we want. So I picked 0 and 1. If you plug in 0, you just get 8, and then here you get 0 plus 4 is 4, so we have 4a, 0 minus 2 is negative 2, minus 2b. There's one little equation. You plug in 1, 5 and 8 makes 13, 1 and 4 is 5, so we have 5a, 1 minus 2 is negative 1, so we have a minus b. So now we need to solve this little system of equations to find a and b. You could do it algebraically, but there's a nicer way. What we're going to do is we're going to put these into our calculators as matrices, because our calculators will solve them really nice and easy. This is a 2 by 3 matrix because it has 2 rows, 3 columns. And so you can see I stole the coefficients, 4, negative 2, and then the answer was 8. It's important the answers have to be over here on the right. And then 5, negative 1, and the 13. So when you do that, you put it in for one of your matrices. Okay, you're going to hit the matrix button on your calculator. You're going to edit it to get a new matrix. You're going to tell it's a 2 by 3, and you're going to fill in the numbers. After that, you quit back out, and then you go back to matrix. This time you hit math, and after you hit the math button, you're going to look for RREF. That's reduced row echelon form. Now, don't do REF, wrong one. We want RREF, the reduced row echelon form. So you hit that button under math for the reduced row echelon form. Tell it that you want the matrix that you just did. So for instance, on my calculator right now, it's in matrix A. So I hit the reduced row echelon form. I hit matrix again. I select matrix A, and out pops this matrix, 1, 0, 3, 0, 1, 2. And what that tells me is that A is 3 and B is 2. So then I have my numerators. So I know that my initial fraction breaks down into 3 over x minus 2 and 2 over x plus 4. You can see I split up the integration because now this is really pretty straightforward integration. We have these little factors on the bottom. Those come out of natural logs. And because the chain rule just gives us a 1, we don't even have to worry about doing anything with the chain rule here. So we just get 3 from the top times the natural log of the absolute value of x minus 2 plus 2 from the top times the natural log of the absolute value of x plus 4. And so that's how these work. They're relatively straightforward. I've got a couple more examples where we're going to make it just a little bit more complicated, but let me get that on the board. All right, so here's my second example. This one has a repeated factor. We have x plus 2 squared in the denominator. So I have the integral 6x plus 7 over x plus 2 squared dx. You can see I finished the problem here, but first let's go over and do our partial fractions. So 6x plus 7 over x plus 2 squared, it should be equal to a over x plus 2. And here's the key. Since we have a repeated factor, that means that this fraction could come out of things that just were over x plus 2, but it's also going to need something over x plus 2 squared so that to have the power that we need. If we just have the x plus 2, then the power will never work. So b over x plus 2 squared. So I multiply through by the common denominator, which gives me 6x plus 7 is equal to a times x plus 2, because one of them goes away. And then for b, both of them go away on the bottom, and we're just left with b, which is super nice. So you can see I plugged in 0 and 1. When I plugged in 0, I got 7 is equal to 2a plus b. When I plugged in 1, we get 13 is equal to 3a plus b. And we can solve that. If you do, you can do a matrix. You can just use the elimination method if you want here. It really doesn't matter because this one's nice and small. But the matrix is easy. Anyway, you get a is 6 and b is negative 5. So I brought that back. So now I have the integral of 6 over x plus 2. And then for b, negative 5 over x plus 2 squared. So the first part I left on this step, I left alone. Still have the integral of 6 over x plus 2 dx. I brought the minus 5 out front. But then here's the kicker. This is not a natural log because we have a square. And so we can actually integrate that, and we don't need a natural log at all. So I rewrote it as x plus 2 to the negative second. So when I did the integration, I get 6 times the natural log of the absolute value of x plus 2. And again, the leading coefficient here is 1, so it works out nice. We don't have to do any fiddling around with the chain rule. For the second one, we're going to raise that power by 1. That's how I get the x plus 2 on the bottom here, because negative 2 plus 1 is negative 1. So there's my x plus 2 on the bottom. And then don't forget, you have to multiply by the reciprocal of negative 1. So just multiply by negative 1, and that's why I have a plus. And there we go. All right, I have one more example. It's big, it's ugly, and it will be fun. All right, one last example. It's a doozy. This one has a quadratic factor. So you can see I have an x squared plus 1 term here in the denominator. So we have the integral of negative 2x plus 4 over x squared plus 1 times x minus 1 squared. So this has loads of fun. You can see I finished the integration down here. We'll come back to that. Let's deal with partial fractions over there. All right, so we have negative 2x plus 4 over x squared plus 1 times x minus 1 squared. That means we get 3 fractions that we have to work with. We have a fraction, 2 fractions for this x minus 1 squared, one with the first power, one with the second power, just like that last example we just did. But for the quadratic, it's going to have a linear piece on top. So it gets to be cx plus d. It's not just a constant. It gets an x, which is a bit annoying. So I cleared the fractions. On the left, that leaves us with negative 2x plus 4. On the right, don't forget you're using 2 x minus 1 factors, so there's still 1 here for the a, even though 1 goes away. So we have a, x minus 1, x squared plus 1. For b, both of those linear factors go away, b times x squared plus 1, and then cx plus d, all times x squared plus 1. So I plugged in 0, 1, 2, and 3 for x. Okay? And when you clean up the mess, you get 4 is equal to negative a plus b minus d. 2, b is just 2, that's nice. For 2, we have 0 is 5a plus 5b, 2c, and 2d. And for 3, we get negative 2 is equal to 20a plus 10b plus 6c plus 2d. Long story short, throw that in a very big matrix. It's going to be a 4 by 5 matrix. Use your calculator, and you get these values for our constants. A is 1, B is 2, C is negative 6, and D is negative 3. So what I did then is I brought it all back. Here's that first one. A over x minus 1, integral of 1 over x minus 1 dx, plus for B, 2, so the integral of 2 over x minus 1 squared dx. And then for the cx plus d, you can see I split it into 2 parts. Okay, it's addition there on the top, so I can make 2 separate fractions out of it, which is going to make life easier. So we have negative 6x over x squared plus 1 and 3 over x squared plus 1. The first one is just a natural log, so we get the natural log of the absolute value of x minus 1. The second integral is just like that, the one we had in the last example. You're going to pull that 2 out. You're going to treat that as a -2, add 1. And when you do, you get 2 over x minus 1. The third one's really fun. It is a natural log, but where u is going to be x squared plus 1. Because guess what then? du is 2x dx. And so we can make a substitution, and when you do, you get -3 times the natural log of that mess on the bottom. Finally, we have the minus the integral of 3 over x squared plus 1 dx. And if you look into your chart of integrals that we had at the beginning of the chapter, 1 over x squared plus 1 is just tangent inverse, so we get -3 tangent inverse of x plus c. That was fun. Hope you enjoyed it. Have a great day.